Does this equation look familiar? This one that I'm circling. I'm not circling. Okay, okay, this one. Here we go. Yeah, so I'm going to have to do this on the board. Okay, so does this equation look familiar? This is the end of the video lecture that you watched. This was the overall partition function. So this first piece is the translation piece. This piece, nRT over P, was the volume that, essentially divided by this piece that the thermal wavelength is inverted. So we're taking the volume divided by the thermal wavelength. Then what is this piece here? That's the rotational partition function. And this is the vibrational partition function. Okay, and then this is the electronic, which is set to 1 because we just have a molecule that doesn't have any degeneracy. So I did this for the hypochlorous acid molecule, that HOCl from Gaussian. So over here, I have this spreadsheet. You can put in the number of moles. So I did one molecule. It's essentially 1 over an Avogadro's number, 1 atmosphere pressure, 298. And here's the molar mass and the symmetry number. And I have the rotational constants from Gaussian. And then scroll down. I have the vibrational modes, 3 atoms. So I got 3 vibrational modes. And these are also out of Gaussian. So what Gaussian calculated in its thermal chemistry section, based on these constants, I calculated in the spreadsheet using this equation up here. Okay, why do I care? Well, Gaussian gives you one number. I have the whole thing now as a function of temperature, so we can see the behavior. That's what I was after. And I wanted to also see if I could get those equations to work, which I did. It was fun. Okay, so here's the first part. This is the translation, Q, TR, and Q rot. So this is the rotation and translation all on this thing here. And I think I have vibration shown, but you can see that it doesn't contribute. So look at this plot. So here at 0 temperature all the way up to room temperature, 298. And I have 2 different y-axes. This is the Q rotation axis, and it goes up to, and Q rotation is the orange line. Okay, and it goes up to 2500, which is what Gaussian showed for the rotation. Now the translation was something like 10 to the 7th, and you can see that on this axis over here. It's the dotted one. Translation is dashed. It goes up to like 1.4 something times 10 to the 7. Now in Gaussian it was 0.14 times 10 to the 8, right? So you remember I had that weird way of doing scientific notation, but that's cool. I've got the Gaussian numbers here using that equation that they told us Gaussian was using. So it's great. I know now they're telling me the truth. Gaussian is using that equation. Not that we really had to check, but the fun part is now we have it as a function of temperature. And we can see on the same plot, this is the vibrational partition function. Okay. It isn't moving, or you can't see it on this scale, either scale. Okay. And so that's Q vibe. And Q vibe is the multiplication of Q, nu 1, nu 2, and nu 3. So I got rid of the rotation and the translation ones, and here are the Q vibes. Okay, and what do the Qs do as temperature goes to 0? They go to 1. That's nice. Okay, and I didn't even have to change. Like if you'll notice this equation up here, this is the actual calculation of that converging infinite series that we had. So we can actually calculate the vibrational partition function exactly. We don't have to assume that the quantum numbers are infinitesimal and switch to an integral. There was an actual analytical solution to that partition function. So it converges to 1 just like it should, and it goes up to a linear NR at high temperatures. But they are starting to move, but not very much. So even at room temperature, when we're talking about it having to be 10 times the vibrational temperature to be active, that means when it starts to approach that linear NR for every vibrational mode, they are moving slightly. But look, the lower frequency vibrations, nu 1 and nu 1 is the only one. It's the lowest energy vibration, and it's at 1.03. There's like a 3% chance there's some molecules in the first excited state, but 97% are in the ground state at room temperature. So it's moving, but not so you'd notice. On the scale of 10 to the 7, you don't notice, right? So, but it's moving, and so that's the difference between these different molecules. Like even in aluminum, it was a little different than the theoretical. Maybe 1% of those electrons are excited, and that's what's given us that little difference. Okay, so let's move over in the spreadsheet a little bit. So this is the partition functions. Okay, we'll scoot up. Now, I want to calculate the energy, and there's a third way to calculate the energy that it didn't show in the notes, and it's this equation here. If you take the natural log of Q and take the slope of that with respect to beta, and beta is 1 over kT, so temperature's in there. If you take this derivative, that will give you the energy. So that's a little weird equation. We need to do two things. We need to take the temperature and invert it and multiply by Boltzmann's constant. So we have beta over here. That's 1 over kT. And then we have to take the natural log of the translation Q and the rotation Q and the vibration Q. So that's what this plot is. And notice that the energy is a negative slope. And so we can see that at low temperatures, these slopes are dramatically changing, but then they become linear, don't they? That's when you're in equipartition. We've switched over from it being a discrete sum to an integral. Okay? And I haven't done anything with the math to make it that way. It just naturally happens that way. And so this negative slope here is going to be 3/2 in R. And the same with this one too. They have the same slope, even though there's a different magnitude for those. So over here, these are the energy components, the molecular energy components, as a function of temperature. So you see the vibration is not contributing to the energy of the molecule at all until you start to get to 200 Kelvin, and it starts to creep up a little bit. But most of the energy of this molecule is being stored in translation and rotational motion. That's pretty cool. We actually can plot where the energy is in a molecule. And this is an asymmetric molecule, so it's a nonlinear. So it has 3/2 of its energy in translation and 3/2 of its energy in rotation, and just a smidge in vibration at room temperature. Okay. And then we come over here to the heat capacity. Let's see. This is just essentially showing you the same thing, the internal energy components. Yeah, here's the heat capacity over here. What is I going to show about that? Oh, yes. So that was calculated using these molecular, like the molecular partition functions. What if we just assumed equipartition, right? The 3/2 R for rotation, 3/2 R for translation. And so you see, this is the error that you're making. So assuming equipartition and not even doing any of these sums and all of that stuff, all this Excel work, I give you water and you do 3/2 R for translation and 3/2 R for rotation. How far off are you going to be? Here at 300 degrees, less than 1% error. Okay. When you get down to 100 degrees, it's worse. It's still not bad. Less than 2% error. Then you get over here to 50 Kelvin. Now you're at 4% error. 20 Kelvin, you're getting up to 10% error. Okay. For this molecule, HOCl. And then here's your heat capacity components. So you have no heat capacity component from vibration. Here's translation and rotation. This is the slope of those energy lines. Okay, 12.5. What is 12.5? Well, it's 3/2 R. It's 3 times 8, which is 24, divided by 2, 3/2. So that's 12. Okay. 12.5 for the rotation, 12.5 for the translation. You add those together, you get the total of 25. Okay, it starts to curve up a little bit when you get above 150, 200 to 300. and then that's coming into this vibrational contribution. So we can calculate these easily. Okay, now I say easily, those equations are pretty ugly, right? But you can do it, and you can check your work, like you can check your work against Gaussian and say, hey, I must be doing it right. I get exactly the same numbers that Gaussian gives me, and so there we go. So I think that's a fantastic spreadsheet. It sort of puts this big equation into perspective, that we can see at any given temperature how much of our energy is in translation, rotation, vibration. And the take-home lesson is everything is in translation and rotation. Okay, but the differences in materials really comes about by either it being like a monatomic gas versus a multi or diatomic gas or more, or a linear molecule versus a bent molecule, because that's going to change the rotations. I mean, once you go from a monatomic to a polyatomic, you're doubling the heat capacity, because you only had translation in monatomic. Now you go to a diatomic and you double, almost, 2 halves, the heat capacity and the energy. Or if you have a triatomic and it's bent, not linear, then you have 3 halves more. So you've doubled the energy it can contain and the heat capacity that it has. So in all of our engine work that we're going to do in a couple of weeks, those are your questions. What's my working gas? What's pushing the piston? If it's helium, it's just a single atom. If it's carbon monoxide or carbon dioxide, it's a linear molecule. That is important. If it's steam, if it's water, that's 3 halves are on the rotation, 3 halves for translation, and it all is important. But those are really the only 3 types of working gases we're going to use: monatomic, linear, or nonlinear. And that's really all you need to know. Because notice nowhere in here is the molar mass. It's just the type of molecule it is. So it's not 3 halves NR with the molar mass in there. It's the number of moles. Now, when molar mass comes in, if I stuff in 50 grams of something, I got to know how many moles it is. But in terms of its energy components, it's just the particle bouncing around. Okay, so that's enough for today.